So now that we have these inequalities at our disposal, we can start trying to prove things. The first thing that we'll try to prove is coercivity of the weak formulation corresponding to the advection-diffusion equation. Now, we kind of expect that this coercivity constant is going to depend on the ratio between how much the advection and the diffusion relate to one another. I've shown you some basic numerical experiments where if the ratio between advection and diffusion becomes very advective dominant, then we start to see funny behavior. So we expect to see some dependence on the ratio between A and kappa in this expression. So the first thing that I'll do is I'll actually rewrite this expression a little bit to already introduce this ratio. And we're going to talk about a normalized version of these equations. So first we normalize these. By dividing the whole expression by the maximum value or the maximum magnitude of our advection field A. So then we get a normalized advection field here. It's supposed to be a tilde, dotted by the gradient of our concentration or our temperature phi, minus kappa divided by the maximum magnitude of A. That's the Laplace operator on phi. It's going to be equal to also sort of a normalized f here. And so we've divided by the maximum magnitude of A in our complete domain. So we also know now that this guy for sure is going to be the magnitude of this guy, magnitude of our normalized advection vector is going to be smaller than or equal to 1 everywhere in omega. So that's something that we'll actually use in a second. Well, actually, maybe not for the coercivity proof, but for the boundedness proof that we'll do. Okay, so and as a boundary condition, we're also going to have to introduce a boundary condition, obviously, and we'll use that phi is going to be equal to 0 on the boundary of omega. Yeah? Now, this is not necessary. We've seen that any other case we can rewrite into a case that is equivalent to this. So the first thing we'll do is we'll have to come up with an appropriate weak formulation. Of our normalized advection-diffusion equation. Now, the trick, of course, is that we multiply by a test function, we integrate over the domain, and we do integration by parts on certain terms. And if we do all that, then we end up with an integral over omega that has this normalized advection dotted by the gradient of phi multiplied by my test function w, plus an integral over the domain of kappa divided by the maximum magnitude of our advective vector times the gradient of phi dotted by the gradient of w. Now, this integration by parts step would introduce some boundary terms, but all those boundary terms end up getting cancelled by our statement that phi is going to be equal to 0 on that boundary. And then the only thing that we have on the right hand side is an integral over omega of this f tilde multiplied by w. Okay, so now this is our bilinear form on phi and w. And this is going to be our linear form on w. And in this video we'll talk about the coercivity of B. So I'll try to answer the question, is B coercive? Yeah, or is it true that if we substitute the same function, and we substitute phi in both slots, that's going to be larger than or equal to some constant times the norm of phi? Well, clearly, well, actually, in what measure do we take the norm here? Well, we know that we need gradients, so this is going to be looking for find phi in H1 and 0 because of the boundary condition, such that this is true for all functions w in H1, 0. So we have to deal with the H1 norm here. Okay, So we're going to treat both terms separately and have a look at them independently. And start with the first advective term. How can we manipulate this term to give us an expression that is useful for us? And, oh, sorry, actually what I want to do, of course, is I want to substitute now phi in both sides of the test function slot and the trial function slot, right? So this is really the term that we're interested in. Now this one is actually not too bad. We can manipulate this a little bit. We can change this gradient, and we can actually rewrite this as half of the integral over omega of the divergence of a tilde times phi square minus half of the divergence of a tilde times phi square. Now, why is this true? If we work out the indices here, then you would be able to write this term, so I'll do this quickly, as half of the divergence of a tilde. So this is sort of a chain rule, times phi square plus half of a tilde dotted by the gradient of phi square. And this is going to be equal to, so this term here is going to be equal to a tilde times the gradient of phi times phi, half plus half times a tilde times phi times the gradient of phi. Well, clearly these are the same, so this is going to be equal to a tilde times the gradient of phi times phi. So that's this term, and this one is being cancelled by this one, such that in the end we have this. Okay, now I have to go back a couple of steps. Illustrations for why this is true. Now this is an expression that we're actually more happy with. And why is that? Well, first of all, in the derivation of our advection-diffusion equation, we made the fundamental assumption that the advective field was incompressible, and that meant that the divergence of A is going to be equal to 0. So this guy is equal to 0. Okay, so now we only have to deal with this term. Now this is the divergence of a vector expression, for which we can use the divergence theorem. So what does that end up saying? It says half the integral over the boundary of our domain of, well, whatever is inside of the divergence, that is a normalized dot n, our normal vector, times phi square. So this is going to be completely equal to one another. And now we're looking for functions phi in h1 0. So all the functions that are 0 on the boundary. So on this boundary, phi is equal to 0. So we actually know that this first term in our bilinear form, if we look for a coercivity property and we substitute phi in both slots, then the result is simply going to be equal to 0. So interestingly, we don't have to deal with this term. Okay, so now we've handled the first term. The first term is going to be equal to 0 in this coercive sense. So then, what about the second term? Well, that's of course going to be now the interesting term. So let's try to manipulate that. So we have kappa divided by A max, for which I'll assume that also kappa is constant, just for the sake of ease of manipulation of the equations. You could do the same thing for a spatially dependent kappa. So this is multiplied by the integral over our domain omega of the gradient of phi dotted by the gradient, well, of phi. We're substituting the same function in both slots. I hope that my mouse is actually visible. Not sure. Okay, so this is going to be equal to kappa times A max of, well, what is this expression? This is actually simply the norm in L2 of the gradient of phi square. So far what we have is that if I substitute phi in both slots of our bilinear form, then the result is going to be equal to kappa times the magnitude, maximum magnitude of this vector field times the L2 norm of the gradient of that function. So this seems like we're getting close. Of course, we're interested in the H1 norm. Sorry, this should also be a square. So somehow we have to change this norm in the gradient of phi to the H1 norm. So what was the H1 norm again? So we're interested in, we want to know, so we want to have B phi, comma phi, it's going to be larger than or equal to C times, well, what is the H1 norm square? The H1 norm square is going to be phi in L2 square plus the gradient of phi in L2 square. That was our H1 norm. So we have already this gradient of phi square in L2, so that's what we have. But we're missing this term. We're missing the L2 norm of the function phi itself. So how do we get this into our equation? Well, we're going to need one of the inequalities that we introduced, and specifically we're going to need the Poincare inequality. The Poincare inequality relates a norm in L2 to a norm in the gradient of u. So let me write this inequality down as well. So we have Poincare, and I'll square both sides already because we'll end up using the square. So we have the square of some constant Cp again, which only depends on our domain omega, which is going to be fixed obviously, times the norm of phi measured in L2 square is going to be smaller than or equal to the norm of the gradient of phi square, also measured in L2. Did I say that right? Yeah. And this is true for all functions phi in H1, 0. Now, we're looking for functions phi in H1, 0, so that's fine. We can use this inequality. So what that means is what I could do is change this by small or larger than or equal to, sorry. I'm going to flip them around. So this is going to be larger than or equal to kappa times A tilde max times now this constant Cp square times the norm of phi in L2 square. So now we started off with something that measured here in the gradient of phi, which is something that we kind of needed. And with Poincare's inequality, we can introduce now this the L2 norm of phi itself, which we also need. So we're somehow going to have to combine these two. We're going to combine this expression and this expression. And what that means is that we're going to use Poincare, but not on the complete expression here on the left, not on the complete expression, but only on a fraction of that expression. So I'm gonna apply Poincare on not on all of kappa divided by the maximum magnitude of A times the gradient of phi. So not on the complete one here, but on q times kappa times that maximum magnitude of our advective vector. And with that, I'll get Poincare inequality saying that that's going to be larger than or equal to, well, Cp q times kappa times Cp square times the norm of the magnitude of the maximum magnitude of our vector factor times phi measured in the L2 sense squared. So if I do this only for this vector q, where obviously q is going to be in between 0 and 1. If I do that only for a fraction q here, well, then I'm left also with a fraction 1 minus q, right? So we have now b of phi comma phi is going to be equal to 1 minus q times what we have. Scroll this up a little bit here so we see both, okay? Times kappa and so that's what that we still have from our original expression, and now we have used Poincare on only the fraction q, which gave us, so now it's going to be larger than or equal to, which gave us this additional part. Okay, so now we're almost done, right? We want to prove that coercivity holds, so we want to have some constant times the norm of the first guy times the norm of the second guy. Well, we have now both those norms in there. We have the norm of the gradient and we have the norm of the function itself. So in order to factor out the constant, what I'm going to do is I'm going to equate these guys to one another, and I'll find the q for which these are actually equal. And then I can factor them out. So I'm gonna look for the q for which well, we have the same multiplicative factor here, right? So I'm not gonna deal with that yet. This one and this one I can pull out. So I'm gonna equate 1 minus q is gonna be equal to q times cp squared. So it's going to give us for some reason in my notes I have to, oh, it doesn't matter, of course. So what do I get here? I get let's move all the q's to the same side. It's going to give me q plus qcp square, or q times 1 plus cp square. So it's going to give me q is going to be equal to 1 over 1 plus cp squared. Okay. So that's the q that I'll use. As long as cp is larger than 1, then no, actually always. Independent of cp, we always have a q that's between 0 and 1. 0 and 1 here, that's what we wanted. So this is a q that I can always use, and then I end up with b phi comma phi is going to be equal, or it's going to be larger than or equal to kappa times the norm of a, and then the maximum one. So this is not the tilde one. I don't know why I'm doing that here. Hope I have not been doing that all the time. I have, great. Wow, doing that for a while. Okay. Yeah. Times 1 over 1 plus cp square times phi in L2 square plus gradient of phi in L2 square. And that is equal to phi in the H1 norm. Okay, so this is our coercivity result. This is what we wanted to prove. We wanted to prove that if we substitute the same function in both slots of our bilinear form, then the result is going to be equal to some constant. So This is now our coercivity constant, Cc, multiplied by the norm of that function measured in the H1 norm. Yeah? So now we have an expression for what that coercivity constant is going to be. Actually, I don't know if this is the tightest bound. We made use of some inequalities. So maybe you can get a better expression for Cc. And what better means in this case is a larger expression, because obviously I can choose a very small expression and prove this. But we're interested in the largest expression for Cc. Now, so I think this is a pretty tight bound in the sense that you can probably not get a much better estimate for our coercivity constant, such that this is indeed true for all choices, for all functions phi in H10 actually. So what do we learn from this? Well, this Cp, that is, again, dependent purely on our domain omega, and there's not really anything that we can do about this. But we have these physical constants up front. We have the ratio between our diffusion and our maximum advection. And we see in particular that the coercivity constant is going to be small if our diffusion is small or if our advection is large. And this is kind of corresponds to what we've seen before. We said that the coercivity constant is sort of a stability notion of our partial differential equation. And it loses stability once we get a small diffusion and a large advection. So I'll actually show that explicitly for some numerical examples in the next video. Because in order to make that claim rigorously, we do not only need coercivity, but we also need certain boundedness properties. And so we'll also prove these boundedness properties for the bilinear form and the linear form. And then we can really start to look at how our PDE starts to behave for different choices of kappa and an advective field. Okay, so for now, I think the important thing here is that you get a feel for what these proofs might look like. So we start with the bilinear form, for which we want to prove this coercivity. We can manipulate certain terms in our bilinear form. Some of them completely drop out, they cancel, they become zero. For other ones, we try to somehow link them to the relevant norms. We try to rewrite them into relevant norm expressions, and at some point we will get stuck, and then we start to have to introduce these inequalities to finish our proofs. And in this case, the only inequality that we needed was Poincare's inequality to relate a norm of the gradient over function phi with the norm of the function phi itself. And then by some final manipulation, you would end up with a coercivity expression. Okay, so I think I might also ask you to do something similar in one of the homeworks. So I hope this is clear. If not, feel free to contact me by email. And in the next videos, we're going to try and do some more examples of this, but then specifically for the boundedness of these operators. Okay, thank you for your attention.